Hello everyone, and welcome to this video, the 19th in the Kerr geodesics series. Now this video follows on from the previous video in this series that deals with a recently published paper on the archive repository where authors have derived analytical solutions that describe time-like and null geodesics in their Kerr space-time. There's an awful lot I fitted into that sentence. Now, the authors have also written a Mathematica notebook that plots these solutions and is freely available to the public. And the Mathematica notebook can be found here. And the paper from the authors developing equations for plotting the Kerr geodesics can be found here. Now, in this video, the second of this two-part series, I'm just going to concentrate on the null geodesics. Last video I did time-like geodesics. These ones will focus on the null geodesics. All right, so I'll just remind you again, the paper can be found here. This will be in the description. And these researchers, AdamCieslik, I hope I pronounced that correctly, Eva Huckman and Patrick Muck, they derive novel analytical solutions describing time-like and null geodesics in the Kerr space-time. And some of those time-like solutions, I just showed you how you could plot them with your own Mathematica at home or wherever you are. Okay, so that's their paper. That's where you can find it. I'll include the link in the video description below the video. Next one, the Mathematica notebook can be found here. Okay, let's move that. Okay, that link is also included in the description below the video. And next one. Okay, just some pointers here. If you're going to use Mathematica, you'll need to import this particular library into Mathematica and install that first. There's a demo file included, which will give you an idea of how to use it. Okay, how to use the package. Now, just another pointer, keep the files together in one folder and launch your Mathematica notebooks from there. Okay, so I'll have it in this folder here. As you can see here, geodesics master, and there's the demo there. And this file here, there is a, I can't find the name, this one here. Keep that in there in order to launch it. All right, let's just have a quick look at the paper again as I did in the last video. Let's give me that excess numbers. All right, now where was I? Okay, so here's the actual paper, Kerr geodesics in terms of Weierstrass elliptic functions. Three researchers. I won't repeat their names again, and I apologise to them if I've mispronounced it earlier. Okay, so we come down here, and their metric convention minus plus plus plus, metric terms here. They set G and C to 1, and so you get these terms here for the metric. Equations of motion, delta 1 for time-like geodesics, 0 for null geodesics. They're using the Hamilton-Jacobi equations, and there's some relations here, dx d tau, where tau tilde is defined as proper time over the mass of the particle. Okay, it's a little bit different there. These equations here involve the Carter constant. They involve this component of the momentum, the time component of momentum, the covariant form, and the phi component of momentum. Both of these are constants of motion. The Hamiltonian is also a constant. You'll see that in the next video, or next two videos I do in the series after this. Normalizing the fall velocity gives you this, minus 1. They've set C to 1 and G to 1. Gravitational constant to 1, but minus 1 in their case. You normalise the fall velocity, and 0 for the fall velocity of a null geodesic, of a particle travelling on a null geodesic, so a photon. All right. The Carter constant is the fourth constant, and these four constants, the Hamiltonian, the time component of momentum, and the phi component of momentum, along with the Carter constant, allows them to come up with these four equations here. And I will derive these for you in the next two videos after this one. Anyway, this constant term r is this object here, theta is this, and so you can write the covariant component of the momentum, or the r component of momentum, as this object here. Epsilon r and epsilon theta are just plus or minus 1, just depending on direction you go. What they then do is they then rescale the coordinates so that you get a rescaling of this to give you this. Okay. S is the Mino time given here. And when they rescale those four equations, these are the ones they work with in plotting them. Okay. Now, these equations, as I said before, use these four constants of motion, 1, 2, Hamiltonian, and the Carter constant. And as I said, the Carter constant, I will make the subject of the next two videos after this, how we derive it. Other than that, they're plotting different solutions here, so I'm just going to leave that for a moment and show you some of those solutions if you've got Mathematica. So let's have a look at a flyby orbit. In all of this video, I'm just going to set the initial angle phi 0.33. Epsilon r will be inward, so it's -1, so it's an inward. So we're going to start the object somewhere off up here. Okay, start the photon or massless particle up here, and it's going to follow a path down towards the Kerr black hole. Distance starting point 25 units. This refers to the polar angle, and this is going to be positive direction, so it's going down this way. Phi was positive, so it's measured from the positive direction of the x-axis, so it's round. This is 25 units up. Okay, epsilon is the energy parameter. Lambda z is the angular momentum parameter about the axis of rotation. So it's the phi component of the form momentum. It's the angular component about the axis of rotation. So it's phi. That's given a constant value. It's a conserved quantity along geodesics. A is the dimensionless spin parameter, varying from -1 to +1. Generally, we think of it as 0 to 1, but if you include spin in the opposite direction, then you would go from -1 to +1. Kappa is energy light parameter. It's a combination of some variables of lambda, the spin, and the energy, the square of all that. Delta 0 is we're dealing with massless particles, so photons, gravitons, or any other massless particle. I have said in previous videos perhaps some neutrinos, but generally it's accepted that neutrinos, all neutrinos have mass because of neutrino oscillation, but any other massless particle besides photons and gravitons, this would be a subject applicable to. So here's a flyby orbit projected onto the XY plane, and here it is in 3D, three-dimensional space. All I'm going to do is I'm just going to change the angular momentum parameter. That's the conserved quantity about the vertical axis of rotation. So it's the angular momentum in a plane perpendicular to the axis of rotation. I'm just going to vary that, change it up and down. Okay, all the others will stay the same. The energy parameter, all of these other starting points, starting angles, everything, spin of the black hole, everything is going to stay the same. But I just want to show you what happens is we just vary this one conserved quantity. You can play around with it once you get a Mathematica notebook. That's all I'm doing. I'm just playing around with it. Okay, so next time we lowered the conserved angular momentum about the vertical axis, just a little bit from 4.7 down to this, and very slight change in orbit, in the flyby orbit. Just going to take my time. I've lowered it again. You can see it's changing just a little bit, not a great deal. lower it again from 3.5 to 2.5. It's tipping over here to the left. It won't tip over as much as you expect, or as much as I expected when I was doing this, but anyway. By the way, each of these simulations on my laptop takes something like 15 to 20 minutes to run. Okay, so 1.5 here, it's tipping over a bit. 0.5, it's tipped over a bit, but not a great deal. But notice it's getting sharper here. See how the black hole is spinning in this direction, this anti-clockwise direction, and the space-time it's dragging around with it is starting to really heavily drag that photon around. It's quite a high spin, 0.8, but not extreme. But it's starting to drag that photon around. You can see the geodesic gets twisted around, and you look at this bump here. Okay, so that's at almost 0. Now watch what happens. When we go to 0.2, sorry, that little bump there gets sharper. You can see the dragging effect, the frame dragging as it twists the space-time around the black hole. And getting close to 0. See how sharp that bump in here is getting? A bit more. Oh, it's almost a point now. 0.02 is getting very close to 0. 0.05. See if it's very sharp there, but now it's gone to 0. Look what happens. It's simply deflected. So great is the twisting the space-time around, it simply deflected the photon off. Whether or not that reflects reality or not, I don't know, but certainly these equations are predicting that. I don't know if that reflects reality or not, whether or not a photon would be come in and then be thrown back out again, because it simply has no angular momentum at all around that vertical axis and gets thrown out again. Whether or not that reflects physical reality, well, I don't know, but the equations that underlie this Mathematica notebook are predicting that. Okay, so let's start going negative, and we just get an inversion of what we had before. So the more negative I go, this bump here on the corner gets smoother, and looking more like flyby minus 4.5 is like what the same sort of thing we started with. Okay, let's have a look at some plunge orbits now. So nothing's changed up here. Nothing's changed. I've changed kappa from 60 down to 12. Yeah, I had 60 there. I've changed it down to 12. Here, say, photon with 0 momentum in the phi direction. 0 momentum component in the phi direction. And it just plunges in. It just follows a plunge orbit. No angular momentum at all. Small amount of positive angular momentum. It starts to rotate with the black hole. Still plunges in though. Larger angular momentum, it rotates but takes longer before it plunges in. A little bit extra here. Smaller angular momentum again, and it just plunges straight in and keeps going all the way in. Now, I'm getting near the end here, and with this one, this is a deflection orbit where it's got a certain amount of angular momentum in the phi direction. All the other parameters are held constant. And it comes in and it's just deflected in its orbit and thrown back out again. You can see that in the three-dimensional case here. Thrown back out again. Very interesting, isn't it? Tend the angular momentum in the phi direction towards 0 and it becomes a plunge orbit. But start increasing away from 0 and you get a deflection orbit. So photon loses enough angular momentum, it can plunge in. If not, it tends to do a flyby or a deflection orbit. I mean, if I had minus 2.5, it'll just come in the other way like this and come out again. That's all that happens if I put negative there. That's it.